All right, for examples 3 and 4, we're just going to use the rational root theorem to identify the roots of each equation. And then I did add some graphs so we can talk about multiplicity once again, just as a little refresher. And then you'll have time to do your homework. So example 3, we have x cubed plus 6x squared plus 12x plus 8. If I want to list out the possible roots using the rational root theorem, it's going to be plus or minus the factors of our constant, so of 8, over plus or minus the factors of our leading coefficient, which in this case is 1. So my possible zeros are plus or minus 1, plus or minus 8, because 1 times 8 is 8, and also plus or minus 2, plus or minus 4, because 4 times 2 is 8. That's all going to be over plus or minus 1, but remember that plus or minus 1 doesn't really affect anything, so I'm just going to leave them as whole numbers so they look nice and neat. We just need to start testing them, because even though these are all of my possible roots, by looking at the degree, I know I can only have 3 of them. Again, I like to pick the small numbers at first just because I'm testing them. I don't want to make the math too hard for myself. Checking for standard form and for any placeholders. Looks like we're good. So 1, 6, 12, and 8. Starting synthetic division. Bring down my 1. 1 times 1 is 1. Add those together, I get 7. 7 times 1 is 7. Add those together, I get 19. 19 times 1 is 19. And whoa, no remainder of 0. So that doesn't work. Okay, well, how about a negative 1? Let's try that. 1, 6, 12, 8. Okay, bring down my 1. 1 times negative 1 is negative 1. Add that together, I get 5. 5 times a negative 1 is a negative 5. Add those together. I can already see just by looking at it, 7 times negative 1. Yeah, that's not going to work. Sometimes when you're doing it, you'll notice that it's not going to work and you can just stop. You don't have to finish it. How about, let's say I wanted to try 2. I want to point something out here real quick. Notice how all of these coefficients are positive. So if I'm testing a positive number, the number is going to keep growing, isn't it? Why don't I try a negative 2 instead of a positive 2? Bring down the 1. 1 times negative 2 is negative 2. Add those together, I get 4. 4 times negative 2 is a negative 8. Hey, it looks like it's going to work because I get 4. Multiply that by negative 2, I get negative 8. That was a 0. Using this, because I've discovered that negative 2 is a root, I'm going to write it in factored form. Remember, the binomial here needs to give me a solution of negative 2. So I actually need to put x plus 2. And then in my next parentheses, I use my new coefficients. So that would be 1x squared plus 4x plus 4. We now have it to a quadratic, which we do know how to factor. I'm just going to use guess and check real quick. The factors of 4 are 1 and 4, 2 and 2. In order to get a positive 4, though, I need to use a plus 2 and plus 2. So that gives me x plus 2 times x plus 2 times x plus 2. Meaning that my zeros, my 3 zeros, because I had a degree of 3, was negative 2, negative 2, negative 2. I have the same number listed 3 times. That means that there is a multiplicity of 3. Because it's used 3 times, and that is an odd multiplicity, I know that is going to pass through the x-axis at negative 2. Let's just check on Desmos and see if that's true. All right, so I pulled up Desmos. Here's my equation right here. The graph does in fact pass through at -2. And also notice how it does have that bend that we talked about, how it slowly approaches the intercept and then slowly goes away, then speeds up. So I just drew my very rough sketch. And I also wanted to point out that because this was x cubed, that's an odd power, I do have different end behavior. The leading coefficient was a +1, so as it moves to the right, it's going up. Taking a look at example 4, I need to start off using the rational root theorem. So I want to put plus or minus my factors of the constant, so 27, over plus or minus the factors of my leading coefficient, which in this case is 1. Now I did it 1 each time on purpose. I'm trying to give you a really basic introduction. So my rational root theorem tells me the possible, keyword here is possible roots, would be plus or minus 1, plus or minus 27, plus or minus 3, plus or minus 9. Even though these are all possible roots, the degree of 4 tells me I can only have 4 possible, or 4 zeros. The best way I can do it is just start testing them. I like to, like I said, use small numbers. So I always start with 1. Now here's the thing though. Do not forget to check and make sure the function is written in standard form with placeholders. I say that because we do have a placeholder here, and if you would have forgotten it, you would not have ended up with the correct solution. So I have 1, 8, 18, and I am missing an x squared, or excuse me, an x. So if I'm going to put a placeholder, I need to put a 0x there. And then minus 27. Okay, let's see. Bring down the 1. 1 times 1 is 1. Add that, I get 9. 9 times 1 is 9. Add those together, I get 27. 27 times 1 is 27. Add it to 0, I just get 27. Multiply it by 1. Hey, right off the bat, it worked. So I'm going to rewrite it as, remember this root here, that 1 needs to be a binomial that will give me 1, so x minus 1. And then in parentheses, I write my new, the quotient. So x, I started off with the 4th power, so now it's x cubed plus 9x squared plus 27x plus 27. And, oh, but when I look at this, normally when we have 4 terms, we say we try factoring by grouping, right? Well, this would have a GCF of x squared, so it's x squared x plus 9. This has a GCF of 27, so 27x plus 1. X plus 1 and x plus 1? That's not the same. Factoring by grouping does not work here. And we did say right in the beginning, factoring doesn't always work. So we have to do synthetic division again. Now, just because I've already used a 1 doesn't mean I can't use it more than once. So all of these, once again, are my possible solutions. So I'm going to try 1 again, just because, I like it. And I'm going to use my new coefficients this time, though. Okay, so we still have all these possible zeros, but I'm using my new coefficients. 1, 9, 27, 27. Bring down the 1. 1 times 1 is 1. 9 plus 1 is 10. 10 times 1 is 10. Add those together, I get 37. Yeah, I can already see that's not going to work, because I'm going to multiply by 37 by 1, and I'd have a positive 37 here, and that's just going to be a big number. That's not 0. So let's try -1. How about that? 1, 9, 27, 27. Let's see here. Bring down the 1. Negative 1 times 1 is negative 1. That gives me an 8. 8 times negative 1 is a negative 8. Okay, I already see this is not going to work either. Remember, like I said, if you see it's not going to work, you can just stop. Let's go crazy and let's try, instead of a positive 3, let's use a negative 3. Now here's why I say that. If I were to do a positive 3 and I have my 1, 9, 27, 27, these are all positive. So without any negatives to start reducing the number's just going to keep bigger and bigger and bigger as I go along. So if I try a negative 3, maybe that can get me to 0. Let's bring down the 1. 1 times negative 3 is negative 3. I'm going to add those together. I get 6. 6 times negative 3 is negative 18. Add those together. I get a positive 9. And then positive 9 times negative 3 is a negative 27. And now we can see that we do in fact end up with 0. So negative 3 is a root. When I rewrite it this time, we cannot forget about that x minus 1. So I need to bring down that x minus 1. This negative 3 gives me a binomial of x plus 3. And then in parentheses, I'm going to write what remains. So x squared plus 6x plus 9. So what we've done here is we've had to use synthetic division twice in order to bring it down to a quadratic, which is what we know how to factor. I'm going to use guess and check since a is 1. Factors of 9 are 1 and 9, 3 and 3. In order to get a positive 6, I must put plus 3 and plus 3. So my zeros, and remember, we start off with a 4th degree, so I should have 4 zeros. That would be 1, negative 3, negative 3, negative 3. So I do have 4 zeros, but that doesn't mean I have 4 x-intercepts. I have 2 x-intercepts. One of them would be at 1, and the other would be at negative 3. So I have 2 x-intercepts with a multiplicity of 3 at negative 3 and a multiplicity of 1 at 1. These are both odd multiplicities, so both of them are going to pass through. I'm going to check Desmos and make sure that that's true. Alright, so I've graphed it into Desmos, and I do see, in fact, that that is true. I have negative 3, positive 1. Both of them pass through, but notice how at negative 3, where we had the multiplicity of 3, it does have that bend that we've been talking about. And also, I wanted to point out, because it's initially x to the 4th power, it has the same end behavior. Both are going up. Going back to the notes, I just drew a picture of my graph showing my 2 x-intercepts and how the multiplicity has impacted that graph.